Hello, and welcome to Conditional Probability and Independence. My name is Tuesday Johnson. This is an introduction to concept with applications. Conditional probability. Let's look at the concept and the formula here. Conditional probabilities are probabilities that are computed that depend on a certain event happening. For example, what's the probability that a student graduates college given that they also work full-time? I know you're working hard here. We're not going to answer that question or anything, right? But you could probably find it after you finish this class. The formula, if A and B are events with the probability of B not 0, then the conditional probability of A given B is probability of A given, that's what this straight line means, B. Probability of A given B is the probability of A intersect B divided by the probability of B. Okay, the given is always in the denominator. So a survey of 100 students that enrolled in finite math found the following information, and here we have it in the table. We want to find the probability that a student passed the class given that they read the syllabus. So we know they read the syllabus. We want to know what's the probability that they passed the class. Well, first we look at the intersection. A student passed and they read. So read and pass. Read the syllabus, passed the class. There are 50 out of the 100 students that did so. Given that they read the syllabus, the probability that they read the syllabus has 55 out of 100. So the probability is 55 out of 100. So now we can put it together. The probability that someone passed the class, given that they read the syllabus, is 50 over 100 divided by 55 over 100. Notice those 100s are going to cancel out there. And so we'll have 50 over 55, which is like a 90% chance that they passed the class if they read the syllabus. I'm just saying, read the syllabus. Notice that the probabilities that we use here, we can just simplify them to the numbers themselves. Since they are all out of 100, we can use just the 50 of the intersection divided by the 55, the number that read the syllabus, and it all works out. And we're going to do that on these next examples. So we want to find the probability that a student did not read the syllabus, given that they did not pass the class. Okay, so they did not read, intersected with not pass. Did not read, did not pass, that's right here, that's 15. Given they did not pass, so what's the number of people that did not pass? Did not pass the class, there are 20. When I put it together, the probability that someone did not read the syllabus, given they did not pass the class, is 15 over 20. That's a 75% chance that they did not read the syllabus if they did not pass the class. Read the syllabus! It's never too late to read the syllabus. It could be the end of the semester. Syllabus still has good information for you. Last one, I promise. Find the probability that a student read the syllabus, did not pass the class. That doesn't say given anywhere. How in the heck are we going to figure this out? So let's rephrase it. A student that read the syllabus. We know they read the syllabus, so that's our given. What's the probability they did not pass the class? So a student did not pass, given they read the syllabus. Probability of not pass, given read. We have not pass, and read is 55. Just the probability that they read the syllabus is 50. Wow. Did not pass is 5. Read the syllabus is 55. 5 out of 55 is 1 out of 11, which is 0.0909. So yeah, like a 9% chance of not passing the class if you read the syllabus. And I totally made up these numbers, but I'm just saying syllabus matters a lot. You got this. Let's talk about independence. The events A and B are independent if the probability of the intersection is equal to the probability of A times the probability of B. And it's cool to be independent. We all dream of that. If two events are not independent, if the probability of their intersection is not equal to the product of the probabilities, then they are dependent, and it's okay to get a little help from your friends. Okay, in 1978, let's talk about independence here. In 1978, the Triple Crown winning Seattle Slew beat the Triple Crown winning Affirmed in the Marlboro Cup at Belmont Stakes, racing alongside 10 other horses. This is fact. You can look it up. Marlboro Cup is no longer ran at the Belmont Stakes, but this is one of only 3 times that 2 Triple Crown winning horses were in the same race. Let's suppose each horse had an equal chance of winning, all 12 of them, right? 10 others, Affirmed and Seattle Slew. If S is the event that Seattle Slew wins and A is the event that Affirmed wins, are the events independent? Let's go to a decision algorithm. Okay, getting a little silly here. Case 1, Seattle Slew wins. Alright, if Seattle Slew wins the race, which they did, Affirmed cannot win, and the probability of Affirmed winning is 0. Okay, so what if Seattle Slew does not win? Well, then there are 11 horses, Affirmed and the 10 others, that could win. Each has an equal chance. Affirmed, one of those horses, the probability that Affirmed wins is now 1 out of 11 if we know Seattle Slew does not win. But if what Seattle Slew does changes what happens with Affirmed, these have to be dependent events. Alright, the probability of Affirmed winning changes depending on what happens with Seattle Slew, and I just said depending on, they are dependent events. This one's getting a little long. I appreciate you listening. Don't forget to subscribe.